Hey guys, this is Alan here to talk a bit about the topic of linear systems. Specifically, linear systems is broken into smaller sections. So we'll start with the concepts of frequency and transient response. So let's get started. All right, first let's talk about transient response. The output of a linear system is comprised of two types of responses. You've got your transient response, and you've also got your steady state response. And it's probably easiest to think of these as like a temporary response. That's your transient response, like it's going to fade away as time increases. And then your steady state response is just that, it's steady, it stays the same. So it's the constant response. This can be expressed using the equation y of t, which is your total response, equals the transient response plus the steady state response. Here you can see a graphical representation of steady state response and transient response. And then to the far right, you can see that when you combine them, you get your total system response. This is maybe a little bit confusing to see how the steady state and the transient add together to give you the system response. But if you just take one point in time and take the values of the steady state response and the transient response at that specific point in time and add those together, you'll see how that gives you the system response. So let's take time as 0. And you can see that right there on the x-axis. Sorry, we don't have it labeled, but the x-axis on each of these is time. So let's take time equals 0. And you can see at the steady state response, that green line at that point is, let's just say that's at a value of 5 something, all right? And then look at the blue curve, and on that one at time equals 0, let's say that's at negative 5. So when you add 5 and negative 5 together, you get 0, and you can see that reflected in the system response curve, the red curve to the right. At a time equals 0, that curve is at the output of 0. So it's just beginning right there. And you can do that for every point on this, and you could test that out just to confirm that the steady state and transient responses together do give you that system response. All right. An important, I don't know if parameter is the right word, but something you may be asked to find for a given response is the steady state error of the response. And what this means is how far off from the desired value is the actual value. So if we had a desired value of 3, 3 anything, who cares what the system is? If that's our desired value and our actual value was 4, then we're off by 1. So our steady state error is 1. Now, it's important to remember that steady state error refers to the error after this system has settled. So systems have different responses, and if you've taken control systems, you know that sometimes the response will oscillate for a period of time before settling at a particular value. And this steady state error refers to how far off that response is after it's had time to settle within 2% of its final value. And so that's your steady state error. The performance of the system can be evaluated by examining the steady state error we just said. Ideally it would be 0, but it doesn't work out that way in actuality. Let's move forward to error constants in a unity feedback system. Now, first we'll probably need to address what a unity feedback system is. So let's take a look at our whiteboard for just a moment. And let's create a block diagram of a feedback system where G of S represents our open loop transfer function. Let's say y of t is our output That's our response. And then through here we've got H of S. And then we're going to come up here, and we're going to have, this would really be a summing junction right here. You could have a plus or a minus or two addition signs, or it just depends on the system. And this, by the way, is supposed to be an arrow, just going that way into the open loop transfer function. And when we talk about a unity feedback system, we just referenced, that's when this H of S just equals 1, right? That's a unity feedback system. Oftentimes that H of S will be values other than 1, and it will mean that in order to find certain parameters, or I don't know if that's the right word, certain characteristics of the transfer function and of the response, you will have to simplify your feedback loop sometimes so that you can turn it into a unity feedback system. If H of S, this block right here, if it equals 1, then you can simplify the circuit. This would just be a line. Alright, that's a unity feedback system. Alright, let's go back now to our slides and look at the error constants in unity feedback systems. The error constant, K sub B, can be found if the open loop transfer function G of S is known. And here we have the 3 equations for the error constant. The first one is for the position value, the second one is for the velocity value, and the third one is for acceleration. Moving forward to poles and zeros in a system response. Poles and zeros, if you've taken control systems, you know that you'll spend a lot of time calculating the poles and the zeros of a particular transfer function. That's the G of S that we saw in that block diagram a minute ago. And these poles and zeros tell you about the system response. Poles are defined as values of S that make a function, G of S, equal to infinity. All right, and that actually, while I was taking the control systems class, is not how I heard it described, but reflecting on what we actually did do, that makes perfect sense, because the poles of the system are whatever values of S that would make the denominator of G of S equals 0. And we know that as your denominator in any fraction approaches 0, then that means the value of the whole fraction approaches infinity. So that is in line with what we were taught there as well. Zeros are defined as values of S that make a function, specifically the transfer function in this case, equal to 0. That just means take your numerator of your transfer function, set it equal to 0, and solve for those values of S's, and you found the zeros of the transfer function. I failed to mention that for the poles. That's what you're essentially doing there also, except you're doing it with the denominator of the transfer function. Take the denominator, set it equal to 0, and solve for S, and that tells you the poles of that transfer function. All right, now let's talk about why those are important. Poles and zeros typically are displayed on a pole zero diagram in the S plane, which is comprised of imaginary versus real axes. Let's go to our whiteboard for just a moment, and I'll show you just real quickly. We'll review what that pole zero diagram might look like. So here you've got your imaginary axis, and here you've got your real axis. And when you make a pole zero diagram, you'll have, your poles will be shown with little X's, and your zeros will be shown with actual zeros. And you could have them scattered about. I'm randomly putting locations of these, to be honest with you. I don't even know if one like that is possible right off the top of my head. I suppose the transfer function could be as crazy as we want it to be. But that's poles, zeros. So let's say this particular pole, I should use a different color for this. Let's say this pole is at the point 0, 2. All right, so you're going to have that. Each one of these has a coordinate pair that it corresponds to. All right, let's go back to our slides now. And on the same slide we were just looking at, the estimated system response can be determined from the pole zero diagram. So the locations of those poles and zeros are very, very important indicators of the system response. If you've got a single pole on the real axis, that means that the system response is going to be one of exponential decay. If you have a pair of poles on the imaginary axis, the system response will be one of undamped sinusoidal oscillation, or underdamped, I should say, and which is unstable, by the way. And if you have a pair of poles left of the imaginary axis, you have a decaying sinusoidal response. And that decaying sinusoidal response is what many of you remember as being an overdamped function. I'm sorry, an underdamped function. And that's actually a good thing, and that is reflective of a stable system because it will in fact settle. And I actually need to correct something I just said. If you have a pair of poles on the imaginary axis and you get that underdamped sinusoidal oscillation, that's not necessarily unstable. All right, let's go forward and let's talk about frequency response. Frequency response refers to the change in the gain and the phase angle as the frequency changes. And the gain is expressed in decibels and the phase angle is expressed in degrees. And here are some important equations that may be needed, and these will be in the FE handbook for the gain margin and the gain and the phase margin. And let's look at these graphically here. You can see that the gain characteristic is a representation of the gain on a plot of output versus frequency, as the frequency, that's omega sub f, as the frequency is changing. So your x-axis is your frequency, your y-axis is your output, and the figures on there, the m sub p is the peak gain of the system, and it will occur at the natural frequency. So wherever the peak is, that's the natural frequency. And then the bandwidth is determined by taking the two output values that are equal to 0.707 of that peak value. And mark those points and then go downward to your x-axis, and all the space in between those two values is your bandwidth. Phase characteristics are found in much the same way as gain characteristics, and phase characteristics are a representation of the phase angle versus the angular velocity displayed on a plot. So they'll look very similar to those that we just looked at. I hope this has been helpful, guys. We've said before that I hope these help, but don't rely on these solely for your FE preparation. And good luck on the FE. Bye-bye.